So today's lecture, as you might have seen, is about hash functions. So last time we had these examples where we talked about this fully random hash function as like an idealized setup that allowed us to analyze hashing with chaining in a simple way. So today we're going to look at practical hash functions you can actually implement and that are actually very efficient in practice. Okay, so the first notion of, I guess, the simplest property a hash function can have. So maybe let's just recall hash functions are just functions h from some universe u. Typically, u is some sort of integers. This lecture, integers, fixed range, and then we map it down to some smaller, typically integer range m here. So we use this notation. M is just a set of integers from 0 to So a hash function here in this course is something that we choose at random before we initialize our data structure or algorithm, right? So it has some random seed that we pick in advance using real random bits. And then from there on, the hash function is fixed. So whenever we evaluate it on a given x, we get the same value every time. And so last time we had this idea of, let's just recap it, right? A truly random hash function, which I think is the strongest property like a hash function can have. And this hash function is basically saying the hash value of any given key is typically, we say it's uniform. This property we like, it's uniform in the output domain here. And also hash of x, so the hash value is independent of all the other hash values. So let's say hash of 0. If I tell you all the other hash values except hash of x, it is still, say it's the domain size of u-1, and it is still uniform random, even if I tell you what all the other values are. So this was this idealized assumption about hash functions, and we also talked about you could actually implement such a hash function if you wanted to by basically initializing a giant array with an entry for every element in the universe. So from 0 up to, let's say again, it's integers up to u-1. So on every entry, you just when you initialize, you just fill every entry with a random number from 0 to m-1, independently of all the other entries, right? So random m. So you initialize this giant table, and then when you want to evaluate hash of x, you just go to entry x and return whatever values is stored here. Then this is independent of all the other hash functions. You have constant evaluation time of this hash function. But the issue is that the amount of memory you're using here is proportionate to the universe size. Right? And so in particular, we saw this example of hashing with chaining where we're building this data structure, right, for storing items. And we're going to use that example again, so I'll just recall it here. So we have a set of keys. In the simplest setup, we just want to store a set of keys S. And there's n of them, let's call them x1 to xn. And they all come from some, see, it says the integers from 0 to u-1. So we have keys we want to store. And then we did this hashing with chaining. The idea would be to store an array, m entries. And in every entry, we have a linked list of all the keys that hash there. Right? And then when we want to check, so we have one operation, this like a membership query, so query for x. This is supposed to return is x in the set S, right? X S. And the way we did it was that we scanned through the list in entry A hash of x. Scan the list in this position to see if x is there. And then we analyze this, in particular, if we use this truly random hash function, then the issue is if we're storing, say, 64-bit integers, the size of this table is 264, right? And the size of this table here is typically, we saw that a good choice was something like m is maybe equal to n. This table, this hash table itself is much smaller than the size of the hash function. And also, if we were anyways allowed to spend memory proportional to the universe size, we could also just store a bit vector that says which of the, with the 1 for every element in the set S, right, and 0 for all the others. Also look up in constant time. It will use less memory than just storing this hash function. So that's the, I guess, motivation for today. We'll try to look at other properties hash functions can have, such that you can still, for instance, solve this dictionary problem with runtime guarantee and something. So the first kind of property that we will be looking at is, I guess, the simplest and weakest property that is still useful for something, and we call this universal hashing. So universal hashing. So here we really only care about these collision probabilities when we're hashing 2 elements. So we say that a hash function h is universal. If for all 2 distinct keys that come from this universe that we're hashing, should be the case that the probability or the random choice of the hash function, so when I pick my random seed to my hash function, the probability that the hash of x is equal to the hash of y should be at most 1 over n. Depends the output size. This is a nice simple property. It's also the property that the truly random hash function has, right? It also has the property, if I look at the hash of 2 distinct elements, the chance the hash to the same is exactly 1 over n. Here we're saying the chance that you hash to the same is at most 1 over n. The difference is for truly random hashing, again, here we require that the hash function of x is independent, even if all the other hash values, all the other values, the hash of x is still uniform random. This is not a requirement of here. Here we're only saying if I look at 2 distinct keys, then the chance the hash to the same should not be equal. That's the difference. Okay. So, and then we have another kind of relaxed version of this, because this might not always be possible to implement exactly this, but there are some efficient hash functions that satisfy something slightly weaker, and we'll also look at that. So this is called C approximate. Approximately universal. Here, think of C as some small constant. So then it has this property here, the probability that if I look at any 2 distinct keys, the probability they hash to the same is no more than C divided by them. This is slightly relaxed requirement. So maybe before we see an example of such a hash function, let's try to see that this definition is actually used. And we can try to look again at our dictionary problem here. This one where we want to scan the list where x hashes to. We scan the list to see if x is among the keys that end up in this position. Right. So maybe we can try to analyze. We talked about last time, right? The time it takes to answer the query is proportional to the length of the list that you hash to, right? So the runtime is proportional to the length of this list. Maybe we call it, I think last time we called it the list at entry A hash of x. This. So maybe we have a random variable x that is the length of this list. And we would like, last time we bounded. First of all, we start out by looking at what is the expected length of the list, right? Because that gives us the expected query time. Later on, we also use the Chernoff bound to bound high probability, the length of this list, and so on. But for now, let us just look at the simple guarantee of what is the expected query time. Can we say something when instead of a truly random hash function, we have either a universal hash function or even one of the C approximate universal hash functions? What can we say about the expected length of the list that we have hashed to? So we can maybe start out as last time, right? If you remember, the idea was to say, oh, this is some kind of complicated random variable. Let us break it into a sum of simpler random variables. And here, I guess it's even more important because last time maybe one could argue that we knew that if it's a truly random hash function, then this length of this list is binomially distributed. So maybe we could say something just from formulas that we know of. But here, we really don't know how this behaves if I have some kind of concrete choice of hash function. So here it's really important that we try to break it into something simpler. So remember again, S is this set of keys, x1 to xn. So let us define these random variables, maybe to distinguish them, let me call them yi. So this random variable yi takes the value 1 if hash of x is equal to the hash of xi, and 0 otherwise. Like this, right? And then we argued last time that the length of the list is just the sum for all our keys of these yi's. Okay? Good. So let us now try to look at the expected value of this, the expected length of this list. So it's the random hash function, choice of the random hash function. Let us just insert what this is. 1 n yi. Okay, so we have this expectation of a sum. What do we do when we have the expectation of a sum? What can we use here to simplify our calculations? Yeah.
Linearity of expectations.
Exactly right. We can use linearity of expectation. Whenever we have the expectation of a sum, if you use linearity of expectation, and the important thing here is that this also does not require that these random variables are independent, right? And here we don't have a truly random hash function, so there might, so we're not necessarily in the case that they're all independent, but linearity of expectation is still valid here. So we can write with equality that this is sum of 1 to n, expectation of yi. And then we had this whenever we had these 0, 1 random variables, was easy to figure out what is the expectation, right? Because the expectation of the random variable is the sum over all the outcomes, the value of this outcome, the random variable times the probability. So we have again the sum 1 n, and then we get 1 times the probability that is 1 plus 0 times the probability 0. That is just equal to the probability it's 1. Right? That's the 0. Now, so this is just the probability for the random choice of the hash function that hash of x is equal to hash of xi. Like this. Okay. And maybe now to keep it simple, let us just look at the case where x is not in S. It's very easy to handle the other case. Here we know that all these terms, x and xi, are different. So if my hash function h is one of these C approximate universal hash functions, what can I say about this? So can I use this property of the hash function now in this setup here? Basically saying, right, for all pairs of distinct keys, the probability they hash the same is the most C order. That's exactly what we had one of this probability over there, right? It's one of these probabilities that two distinct keys hash to the same. So for analyzing this probability, it's sufficient to just have this C approximate universal. We don't need true randomness to continue from here. So let us use the C approximate just to use the weakest guarantees. Then this is less than equal to the sum of 1 n C over m, and this is just n C over m. So in particular, if we get the array size here n, then if m is equal to n here, then this is equal to just, if C is a small constant, then the expected length of this list is at most C. So we actually get this expected constant time with this nice property up here of just this approximate universal distribution. That's sufficient to get expected constant time. Okay. Before we get to a concrete choice of such a universal or concrete implementation, let's see one more use case of universal hashing. It's also kind of interesting. So the second use case is called, I guess, for signatures. let's look like this. So maybe let's try to imagine some setup where we have a really large universe. This is kind of where this is motivated. So U is very large. Maybe you can imagine that perhaps you're storing, maybe you're creating some kind of shared file directory or something like that, like Dropbox. You're storing a lot of files, and maybe when you have some file locally and you want to upload it to the server, maybe you want to check if it's already there. Makes sense, right? I want to upload my file. If it's already there, then I don't actually need to send the whole file to the server. Right? Then it would be convenient if I could send a short description of my file that allows the server to check whether this file is already there. Maybe we can think of the universe here is like all files, it's all the contents of files up to 100 megabytes or something like that. And then we would like to, what we'll do with signatures is we'll try to come up with a hash function that allows us to do this check more efficiently. Right? So we don't have to send the whole file to get a good idea of whether or not it's already there. Okay, so let's say we pick one of these universal hashing or C approximate universal hash function. Big H. And this hash function is stored both at the server and locally. So maybe this server here is like a file server, say. File server has a bunch of files it's storing, and for every file, it is storing the hash of the contents of the file. So maybe here, so we have all these files, and we're just storing all the hash values here. So you're storing hash of x1 up to hash of xn. So we have n files. We're just storing their hash values. These are just some keys. And this is from U to some output domain. And let's say here, for concreteness, that we're hashing for an output domain of, say, size n cubed. So what we're storing here are all these hash values. How long is such a hash value in terms of bits if we're storing it? Well, a number in this range, right, takes log of number of bits in hash of xi is log base 2 of n cubed. It's 3 log n. This is not that many bits. In particular, let's imagine that you're storing, even if you're storing thousands of files here, say 1024, then log n is 10. So maybe it's 30 bits that you're storing. It even fits in an integer in most programming languages, right? So this is a very small signature compared to maybe a whole file could be hundreds of megabytes large. So it's a very small representation of this file. So what you do now when I have another file here and I want to check if it's already in this file server, what I do is I compute the hash of x, and then I can send it to the server, and the server can check whether hash of x equals one of these values. If it does, then I guess as we'll see, there might or might not be a collision, because you could have two different elements that actually hash the same. It happens sometimes. But so whenever we could say, when I hash my x and I see that they're equal, maybe I need to do a little bit more work, and if they're different, then I know for sure it's not on the file. Does it make sense? You can do like a check really quickly by just comparing these hash values. Maybe another example could be maybe you have a blacklist of web pages that you know you're not that kind of contain scam or whatever. So maybe you want to ask before you're entering a URL, you want to check, is this page blacklisted? Maybe it's a long URL. You can send a hash of the URL to some server that has a list of all blacklisted URLs. It checks whether it's there, and if you have a match, you can send back, okay, seems to be a match between your URL and some blacklisted URL. In this case, you can maybe send the full URL and check whether it actually equals one of these blacklisted ones. And in most cases, you're not accessing any invalid or a blacklisted page, right? Most of the time, you're accessing normal web pages. And if you see that it's not equal to any of them, then you're safe. Does that make sense? Maybe that's a little bit better example, but I guess with a file server, if you want to store it there and you see that it's already there, then you have to send the full contents to a check. So maybe let's say it's a blacklisted server instead. Oops, doesn't erase that. I think that's a little bit better. So let's say it's blacklisted files. I think that's more reasonable. Blacklisted files. So you send your URL, a hash of URL to the server. It checks whether it equals any of them. If it doesn't, it just sends you one big back. You're safe. You can access your web page without sending the full URL. If it says there's a match, then maybe you can send the full URL, spend a little bit more time to verify whether it actually equals one of them. Makes sense? So then we would like to argue that at least if I'm not blacklisted, then it would be kind of rare that I have to send the full URL to the server. Right? So we can analyze this. What is the chance that this hash value equals one of these hash values that are stored at the server if I know that if X is not among them? Right? So here we could say, so you can use this union bound that we saw last time. So now we could define an event, say, so one of these bad events that we talked about. So then we have something that we would like to say doesn't happen, right? We typically try to define some bad events. So we say event EI is an event that happens if hash of X is equal to hash of XI. Right? And right now we're looking at the case X is not among them. Not in the set of X1 to Xn. If X is among them, the hash values will always equal, and you will do the full check, right? So it's the interesting case is that you have some web page that's actually a valid web page to access. You want to check what is the chance that I have to do some extra work to verify that this is fine. Okay. We have this event EI, and then we would like to argue what is the probability that it equals any one of them. Right, so this is same as what is the probability for the random choice of the hash function that there's at least one of these blacklisted URLs where your hash value equals that hash value. What did the union bound tell us we could do with the probability of a union of events? Anyone remember? Yeah.
Number bounded by its probability, or the sum probabilities of each event.
Yes. This is no more than the sum over all the events, the n of them, the probability EI. And then we can write out what this is. Probability hash of X, hash of XI. And so here, I guess we could say, so now what is this probability? If it's C approximately universal, it's at most C over the output domain. So here it was n cubed, so then it's less than equal to the sum over I, C over n cubed. So there's only n terms in the sum, C over n squared. It's a very small probability. I guess with signatures, you could also say, what if I have n elements and I would like to say that no two of them get the same hash value? Then I could also define events. Okay, so this is already sufficient, right, for this check the server, right? You already saw that probability that I, by accident, have a hash value that equals any one of them is at most d over n squared. You could also say these signatures could also be used. I have a collection of n elements. I want to give them shorter names, and I want to have the property that no two elements get the same name. And that's a different use case of this. So let's maybe have that. We have that down here. So let's say we would like hash of X. So this is another example. We want to say that all these hash values are distinct, so then we can use these shorter names to represent our objects. Makes sense also that this would be nice, and we just use this 3 log n bit string to kind of identify our elements. So here we could also define events EIJ for every pair of distinct keys. To be what is this event hash of XI is equal to hash of XPA. And then we can again talk about the probability of the union over I less than j, so all pairs. What is the probability that there's even a single pair that gets the same hash value by accident? union bound less than or equal to sum over I less than j. The probability they hash to the same is C over n cubed. The number of distinct pairs with I less than j is this n choose 2. And this is no more than n half, or n squared half. Right, so this is something like D over 2n. Because again, there's a very small probability that there's even a single pair that hash to the same. Right, so this gives one more use case of this C approximate universal hashing, or just universal hashing. You can use it to get the right expected query time for a hash with chaining. You can use it to do these checks if some element is among a large set of elements. Kind of good first check that if it's not, we'll learn that it's not just by looking at the small hash values. Once in a while, we might need to do a full check. And we can also assign distinct IDs to a set of n keys. And you look at the union bound and see there's a good chance that there's not even a single pair that collide. Right? So there are tons of nice applications of just this simple property of universal hashing. So let us next try to see some concrete implementations of universal hashing.